Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is the superposition theorem as applied to AC circuits. Our objective is to examine several illustrated examples of the superposition theorem. This lecture operates under the presumption the viewer has more than a passing familiarity with the superposition theorem as applied to AC circuits, as illustrated in the AC superposition theorem lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Operating under the presumption you have watched the aforementioned lecture, you're no doubt aware that the superposition theorem is the repetitive analysis of a circuit including multiple sources from the perspective of an individual source contribution, where individual results are then summated, accounting for magnitude, phase shift, polarity, and direction. Employing the superposition theorem is a relatively straightforward process. The general steps are as follows. First, a user must identify a single source of interest. Then, one must remove all other sources from consideration. Voltage sources are removed from consideration by substituting a short circuit or low impedance path through which substantial current will flow in preference to other higher impedance paths. Current sources, in contrast, are removed from consideration by substituting an open circuit or infinite impedance path through which no current will flow. Take note that the addition of shorts and opens in the original circuit may fundamentally alter the nature of the as-analyzed circuit. It may help to redraw the circuit at this point. Then, one performs circuit analysis of the modified circuit, solving for the desired electrical properties. Take note of not only the resultant magnitude and phase shift, but also the polarity and direction of the desired electrical properties. It may help to indicate direction and polarity with arrows. Then, one repeats the above process for all other sources. Once you perform these same steps for all other sources, one then summates all linear properties like voltage and current, taking into account magnitude, phase shift, polarity, and direction. Nonlinear properties like power can be solved for at this time using the final summated voltage and current figures. Mastery of the AC superposition theorem necessitates active participation on your part, and as such I'm encouraging you to please pause the lecture when asked to do so and attempt the example problems on your own. If your answers do not match those illustrated, by all means, feel free to rewind the lecture and correct any mistakes you may have made. Our first illustrated example problem features a series parallel combination of two sources and three impedance elements. Voltage source EA has a value of 5 volts at an angle of 30 degrees. Voltage source EB has a value of 20 volts at an angle of 0 degrees. Impedance element Z1 has a value of 50 ohms at an angle of 0 degrees. Impedance element Z2 has a value of 20 ohms at an angle of 90 degrees. And finally, impedance element Z3 has a value of 60 ohms at an angle of negative 90 degrees. Stage 1 of this illustrated example problem necessitates we solve for voltage across and current through each impedance element when voltage source EA is the source of interest and voltage source EB has been removed from consideration. In addition to solving for magnitude and phase shift, clearly indicate the assumed direction and polarity. Once we've got these values, we'll move on to stage 2 and examine voltage and current figures when voltage source EB is the source of interest and voltage source EA has been removed from consideration. By all means, pause the lecture and try stage 1 on your own. If you're tracking, you should have obtained the following results. Voltage source EB is removed from consideration by substituting a short circuit or zero impedance path. An application of Kirchhoff's current law for the as-analyzed circuit illustrates that source current equals current through impedance element Z1. Current then splits into two paths. Voltage polarity across each impedance element would be as indicated. A Kirchhoff's voltage law analysis of this first loop in orange illustrates that EA equals V1 plus V2. A Kirchhoff's voltage law analysis of this second loop in yellow illustrates EA equals V1 plus V3. Finally, a Kirchhoff's voltage law analysis of this third loop in green illustrates V2 equals V3. These analyses imply that impedance elements Z2 and Z3 are in parallel with one another, a simplification I'm calling Z single prime. Z2 and Z3 taken in parallel present an impedance of 30 ohms at an angle of positive 90 degrees. Impedance element Z1 and our combined impedance Z single prime are in series with one another. This is a perfect setup for the voltage divider rule. An application of the voltage divider rule demonstrates V1 to be 4.3 volts at an angle of negative 1 degree. Assume polarity is positive to negative, bottom to top. Application of Kirchhoff's voltage law demonstrates that V single prime is 2.6 volts at an angle of 89 degrees, or assumed polarity is positive to negative, top to bottom. Combined impedance Z single prime is the parallel combination of impedance element Z2 and Z3. Voltage across elements in parallel is the same. V single prime equals V2, which equals V3. Let's now examine current. Application of Ohm's law demonstrates that current through impedance element Z1 is 85.7 milliamperes at an angle of negative 1 degrees, traveling bottom to top. Another application of Ohm's law demonstrates that current through impedance element Z2 is 128.6 milliamperes at an angle of negative 1 degree, traveling top to bottom. Finally, application of Kirchhoff's current law demonstrates current through impedance element Z3 to be 42.9 milliamperes at an angle of 179 degrees, traveling top to bottom. This completes the analysis from the perspective of AC voltage source EA. Let's put these values aside and do the same thing for voltage source EB. Stage 2 of this illustrated example problem now dictates we solve for voltage crossed and current through each impedance element when voltage source EB is the source of interest and voltage source EA has been removed from consideration. Again, an addition to magnitude and phase shift clearly indicate assumed direction and polarity. Once we've got these values, we'll then move on to stage 3 and summate our results accounting for not only magnitude and phase shift, but also polarity and direction. By all means, pause the lecture and try stage 2 on your own. If you're tracking, you should have obtained the following results. Voltage source EA is removed from consideration by substituting a short circuit or zero impedance path. Application of Kirchhoff's current law demonstrates that source current equals the current through impedance element Z2. Current then splits into two paths. One path which leads through impedance element Z1 and the other path leads through impedance element Z3. It can be said that source current equals I2 equals I1 plus I3. Given the assumed direction of current travel, voltage polarity would be as indicated. Application of Kirchhoff's voltage law to this first loop in red indicates EB equals V2 plus V1. Application of Kirchhoff's voltage law to the second loop in orange indicates EB equals V2 plus V3. Finally, application of Kirchhoff's voltage law to this third loop in yellow indicates V1 equals V3. These analyses imply that impedance elements Z1 and Z3 are in parallel with one another, a simplification I'm calling Z double prime. The parallel combination of impedance elements Z1 and Z3 presents an impedance of 38.4 ohms at an angle of negative 39.8 degrees. Impedance element Z double prime is in series with impedance element Z2. This is again a perfect setup for the voltage divider rule. Application of the voltage divider rule demonstrates V2 to be 13.4 volts at an angle of 98.8 degrees, oriented positive to negative, bottom to top. Application of Kirchhoff's voltage law demonstrates that V double prime is 25.7 volts at an angle of negative 31 degrees, oriented positive to negative, top to bottom. Given our combined impedance Z double prime is the parallel combination of impedance elements Z1 and Z3, it can be said V double prime equals V1, which equals V3. Voltage across elements in parallel is the same. Let's now take a look at current. Application of Ohm's law demonstrates that current through impedance element Z2 is 669.7 milliamperes at an angle of 8.8 degrees, traveling bottom to top. Another application of Ohm's law demonstrates current through impedance element Z1 is 514.5 milliamperes at an angle of negative 31 degrees, traveling top to bottom. Finally, application of Kirchhoff's current law demonstrates current through impedance element Z3 to be the remaining 428.7 milliamperes at an angle of 59 degrees. This completes the analysis from the perspective of voltage source EB. Let's now summate our values. Stage 3 of this illustrated example problem now dictates we summate the values of our previous analyses, accounting for not only magnitude and phase shift, but also assumed polarity and direction. By all means, pause the lecture and try stage 3 on your own. If you're tracking, you should have obtained the following results. Summating the contributions of the two sources is relatively straightforward if one has a modicum of organizational skill. Remember, one must account for not only magnitude and phase shift, but also assume polarity and direction. Note impedance element Z3 experiences voltage of the same polarity and current in the same direction for both sources. When these two aiding effects are superimposed upon one another, these effects would be additive. In contrast, node impedance elements Z1 and Z2 experience voltage of opposite polarity and current in the opposite direction for the two different sources. When these two opposing effects are superimposed upon one another, these effects would be subtractive. Since voltage source EB's contribution has the larger magnitude, let's consider its assumed polarity and direction as dominant. Using this interpretation, voltage source EA's contribution would be subtracted from voltage source EB's contribution. By the way, you are totally free to consider the opposite interpretation and assume EA's contribution is positive and EB's contribution is negative. However, realize any result using this alternative interpretation would also include a 180-degree phase shift indicative of the flipped polarity and direction. Regardless, the magnitude would still be correct. My advice is to simply assume the contribution with the larger magnitude is positive, in this case voltage source EB, and the contribution with a smaller magnitude is negative, in this case voltage source EA. Once you've chosen a direction, just stick with it and don't change your mind. Operating under this assumption, you should have obtained the following values. The opposing contributions of EA and EB yield V1 to be 22.1 volts at an angle of negative 36.5 degrees, oriented positive to negative, top to bottom. Current I1 is 442.3 milliamperes at an angle of negative 36.5 degrees, traveling top to bottom. The opposing contributions of EA and EB yield V2 to be 10.9 volts at an angle of 101.2 degrees, oriented positive to negative, bottom to top. Current I2 is 543.4 milliamperes at an angle of 11.2 degrees, where the assumed direction of travel is bottom to top. Finally, the aiding contributions of EA and EB yield V3 to be 24.5 volts at an angle of negative 25.8 degrees, oriented positive to negative, top to bottom. Current I3 is 409 milliamperes at an angle of 64.2 degrees, where assumed direction of travel is top to bottom. Alright, I believe we've accomplished our desired goals and can move on to the next illustrated example problem. Our second illustrated example problem features a series parallel combination of two sources and three impedance elements. Voltage source EA has a value of 24 volts at an angle of 0 degrees. Current source IB has a value of 50 milliamperes at an angle of 0 degrees. Impedance element Z1 has a value of 109 ohms at an angle of 0 degrees. Impedance element Z2 has a value of 57 ohms at an angle of negative 90 degrees. And finally, impedance element Z3 has a value of 86 ohms at an angle of 90 degrees. Stage 1 of this illustrated example problem necessitates we solve for voltage across and current through each impedance element when voltage source EA is the source of interest and current source IB has been removed from consideration. In addition to magnitude and phase shift, clearly indicate assumed direction and polarity. Once we've got these values, we'll move on to stage 2, examine voltage and current figures when current source IB is the source of interest and voltage source EA has been removed from consideration. By all means, pause the lecture and try stage 1 on your own. If you're tracking, you should have obtained the following results.